Hello, welcome to lesson 15. In this lesson, we are going to look at some more examples on real and apparent depth. We shall also look at the determination of refractive index of a glass block using the apparent and real depth method or the traveling microscope, and shall also look at the determination of refractive index of a liquid using real and apparent depth method or using a traveling microscope. Let's begin by looking at this example. A small object is placed 20 centimeters in front of a concave mirror of focal length 15 centimeters. A parallel-sided glass block of thickness 6 centimeters and refractive index 1.5 is then placed between the mirror and the object. Find the shift in the position and size of the image. Position and size. So here we have an object placed in front of a concave mirror. So we shall have something like this. So we have this object, a real object is placed in front of a concave mirror before we place the glass block. So it will be forming an image. But then also after that we shall again place this glass block of thickness 6 centimeters. So they want us to get the shift in the position of the image and in the size of the image. So before we place the glass block, we are going to find out the position of the image before placing the glass block. So we shall use the mirror formula to get that position. So that is going to be 1 over f is equal to 1 over u plus 1 over v. So the object distance is going to be this u, which is actually 20, and then the focal length of that mirror is 15. So we shall replace here 15 and then 20, then you make 1 over v the subject, and that will give us that. When we make 1 over v the subject and cross multiply, we shall get v as 60 centimeters. So v is going to be 60 centimeters, so it's going to be a real image. Then after that, we can also get actually the magnification of that. We can get the magnification, which is m is equal to v over u, which will give us 60 divided by 20, which is equal to 30. Sorry, which is equal to 3. So the magnification is 3. Now we are going now to place the glass block. So when we consider now the glass block, now the ray which was moving directly to the mirror is now going to meet this glass block, and therefore it is going to undergo a refraction and again a refraction. So because of that, there is going to be a displacement. So this ray which is meeting the mirror is going to be appearing to come from this point, which is O prime. That means that there has been a displacement, and that displacement was caused by the glass block. So that displacement is going to be a displacement O prime, which is a displacement D. So we need to get the displacement D so that we can get a new position of the object at O prime. So if you apply the formula for displacement, that is the displacement D is equal to T into brackets 1 minus 1 over N. So that's the formula for displacement. Then the thickness, they told us it is 6, so we shall put 6 here. The refractive index is 1.5, and then we shall get 2 centimeters. So the displacement here is 2 centimeters. That means that the new u, that is u prime, is going to be the u here minus this d. So that is going to be 20 minus 2, which will give us 18. So we can now apply that formula, the mirror formula, to get the new v, for this u here. So we shall apply the mirror formula on that. Remember, we have the u is the u prime is 18, and we have the focal length does not change, it's still 15. So we can get the new v using the mirror formula still. So when we replace that, we need the v prime. So we shall make v prime the subject from there, and then we shall get v prime as 90 centimeters. So the new position of the image is going to be 90 centimeters. It's going to be 90 centimeters, the new position of the image formed when we have placed the glass block. So if you want to get the new magnification, you shall have 90 divided by 18. That is going to be the new magnification. Now let us get the shift. The shift in the image position is going to be the new image position minus the previous image position before we place the glass block, which is going to be V prime minus V, which will be 90 minus 60, and that will give us 30. So that is the shift in the image position. And in the magnification, the new magnification is going to be V prime divided by U prime, which is 90 divided by 18, which is going to be 5. That's going to be the new magnification. Let's look at the determination of the refractive index of a glass block using real and apparent depth, or using a traveling microscope. So here this is the method where we are using real and apparent depth, but we are mainly going to use this instrument, this traveling microscope. So what are we going to do in this case? We are getting the refractive index of glass block. Before we place the glass block, we are going to make a mark on a white sheet of paper. The setup is going to look like that. We are going to first get a white sheet of paper and make a mark on that white sheet of paper. After making a mark on the white sheet of paper, we are going to focus or place that mark below the traveling microscope, and then we focus the mark using this traveling microscope until when the mark is clearly seen on the traveling microscope. Then we record the reading on the scale, and that reading is going to be recorded as A. After that, we are now going to place the glass block on that mark, on the top of that mark, and again we are going to adjust this traveling microscope until when we can see the mark clearly. Then we shall again record a new position on the scale, the new reading on the scale. We shall read that new reading, and that is going to be B, still in centimeters. Then after that, we are going to sprinkle lycopodium powder on the top of this glass block. On the top of that glass block, we shall sprinkle lycopodium powder, or you can even sprinkle chalk dust if you don't have lycopodium powder. And then after sprinkling it, we are going now to focus that lycopodium powder. We are going to focus that lycopodium powder, and we shall read, when after seeing it clearly, after seeing the particles of the lycopodium powder clearly, we shall read that scale reading here. And that scale reading, we shall read it as C centimeters and shall record it. Then after that, the refractive index, we are going to calculate the refractive index from the formula N is equal to C minus A divided by C minus B. Let us also look at the determination of refractive index of a liquid using real and apparent depth, also still using a traveling microscope. So this one can be called using you can say determining the refractive index of a liquid using a real and apparent depth, or you can say using a traveling microscope. So let us have this setup. This is the final setup. Now how do we use this? First of all, we are going to get a glass beaker, make a mark on the glass beaker. We can scratch at the bottom of the glass beaker. We scratch at the bottom of the glass beaker. Then after that, we are going to place that glass beaker under this traveling microscope. So we shall place it under this traveling microscope and then adjust the traveling microscope until when that scratch is clearly seen, or that mark is clearly seen. And then we make the reading on the scale. We make the reading on the scale as A in centimeters. Then after that, we are now going to pour in the liquid whose refractive index we want to determine. Of course, this liquid is usually a transparent liquid. we usually get the refractive index of a transparent liquid. So we shall pour that liquid in the beaker and then again focus the scratch using the traveling microscope until when it is clearly focused or clearly seen, and then we shall make the new scale reading as B, still in centimeters. After that, we are now going to pour some or sprinkle some lycopodium powder on the top of this water, or you can sprinkle any liquid, any powder or anything which can float on this water. Anything which can float on this water, you can sprinkle on that water, on that liquid. Anything which can float on that liquid, you can sprinkle. And then we are going now to focus the particles, those particles of that powder we have sprinkled, maybe lycopodium powder or chalk dust. You are going to again focus those particles until when they are clearly seen through the microscope. Then after that, again, we are going to record the new scale reading on the traveling microscope, and that is going to be C centimeters. Then again, we are going to determine the refractive index of that liquid using the formula N is equal to C minus A divided by C minus B. That's how we shall determine the refractive index of that liquid. Let us look at some example here. A microscope is focused on a mark at the bottom of a beaker. Water is poured into the beaker to a depth of 8 centimeters, and it is found necessary to raise the microscope through a vertical distance of 2 centimeters to bring the mark again into focus. Find the refractive index of the water. So they have given us the depth is 8, so the thickness is going to be 8 centimeters. And then they have also told us that when the water was poured, we had to raise this thing to 2 centimeters. That means that the displacement is 2 centimeters. You had to raise the microscope through a vertical distance of 2 centimeters. So the displacement is 2 centimeters. The displacement caused by the water is 2 centimeters. So it means that we shall use the formula N is equal to T divided by T minus D, where T is 8 and D is 2. And therefore we shall replace that and we shall substitute for T and D, and we shall have 8 divided by 8 minus 2, which will give us 1.33. So the refractive index of water is 1.33. Thank you for your attention. We meet in the next lesson.